Welcome back to Lesson 9, which is a continuation of our discussion of the domain name system. This course is based on the textbook Computer Networking, a Top-Down Approach by Jim Couros and Keith Ross. So let's get started. In order to deal with the issue of scale, the domain name system uses a large number of services, organized in a hierarchical fashion and distributed around the world. No single DNS server has all the mappings for all the hosts in the Internet. Instead, the mappings are distributed across multiple DNS servers. There are three classes of DNS servers: root DNS servers, top-level domain DNS servers, and authoritative DNS servers organized in a hierarchy. For all domains in the lower levels, the top-level domain is the last part of the domain name. That is, the last label of a fully qualified domain name. For example, in the domain name www.example.com, the top-level domain is com. The client then contacts one of the top-level domain servers, TLD servers, which returns the IP address of an authoritative server for Amazon.com. Finally, the client contacts one of the authoritative servers for Amazon.com, which returns the IP address of the host name www.amazon.com. Let's take a closer look at these three classes of DNS servers. In the Internet, there are 13 root DNS servers, labeled A through M, most of which are located in North America. Although we have referred to each of the 13 root DNS servers as if it were a single server, each server is actually a network of replicated servers for both security and reliability purposes. There are actually very many root servers online. The top-level domain servers are responsible for the top-level domains such as com, org, net, edu, and gov, and all of the country top-level domains such as UK, FR, CA, and JP. The company Verizon Global Registry Services maintains the top-level domain servers for the com top-level domain, and the company EduCause maintains the top-level domain servers for the edu top-level domain. Every organization with publicly accessible hosts such as web servers and mail servers on the Internet must provide publicly accessible DNS records that map to the names of those hosts to the IP address. An organization's authoritative DNS server houses these DNS records. An organization can choose to implement its own authoritative DNS server to hold these records, or the organization can pay to have these records stored in an authoritative DNS server of some service provider. Most universities and large companies implement and maintain their own primary and secondary authoritative DNS servers. There is another important type of DNS server called the local DNS server. A local DNS server does not strictly belong to the hierarchy of servers, but is central to the DNS architecture. Each ISP, such as a university, an academic department, an employee's company, a residential ISP, has a local DNS server. When a host connects to an ISP, the ISP provides the host with the IP addresses of one or more of its local DNS servers. You can easily determine the IP address of your local DNS server by accessing the network status window in either Windows or Unix. A local DNS server is typically close to the host, possibly on the same LAN as the host. A residential ISP is typically separated from the host by no more than a few routers. When a host makes a DNS query, the query is sent to the local DNS server, which acts as a proxy forwarding the query into the DNS server architecture. Suppose the host requires an IP address of an edu website. The query message contains the host name to be translated. The local DNS server forwards the query message to the root DNS server. The root DNS server takes note of the edu suffix and returns to the local DNS server a list of IP addresses for top-level domain servers responsible for edu. The local DNS server then resends the query to one of those top-level domain servers, as you see here. The top-level domain server takes note of that edu suffix and responds with the IP address of a DNS server for the institution. Finally, the DNS server resends the query message directly to the local's institutional DNS server, which responds with the IP address of the host desired. Note that in this example, in order to obtain the mapping for one host name, 8 DNS messages were sent, 4 query messages and 4 reply messages. We'll soon see how DNS caching reduces this query traffic. Our previous example assumed that the top-level domain name server knows the authoritative DNS server for the host name. In general, this is not always true. Instead, the top-level domain server may know only of an intermediate DNS server, which in turn knows the authoritative DNS server for the host name. In theory, a DNS query can be iterative or recursive. In that last slide, we saw an origin host query a server, and the server respond to the host with an IP address of another server, and then the original host query the new server, and that would in turn responds with an IP address of another server, and then the same process is repeated until the origin host actually gets the address it needs. This is an example of an iterative query. This slide that you're looking at right now shows a DNS query chain for which all the queries are recursive. That is, the original host queries the first server, which in turn queries the second server, which in turn queries the third server, and so on until it reaches the server that actually has the IP address that the original machine is looking for. Then that address is returned in order back down that whole queue until the origin host has it. In practice, from the requesting host to the local DNS server is recursive, and the remaining queries are iterative. DNS extensively uses DNS caching in order to improve the delay performance and to reduce the number of DNS messages bouncing around the internet. The idea behind DNS caching is very simple. In a query chain, when a DNS server receives a DNS reply containing a mapping from a host name to an IP address, it can cache the mapping in its local memory. Because the host and mappings between host names and IP addresses are not permanent, DNS servers discard the cached information after a short period of time. The DNS servers that together implement the DNS distributed database store resource records, or resource records, depending on your accent, including the resource records that provide host name to IP address mappings. Each DNS message carries one or more resource records. A resource record contains the following fields: name, value, type, time to live. Time to live, TTL, is the time to live for the resource record. It determines when a resource should be removed from cache. In example records given next, we'll ignore the time to live field. The meaning of name and value depend on the type. If the type equal A, then name is a host name and the value is the IP address of the host name. If the type is NS, then name is a domain such as Amazon.com and the value is the host name of the authoritative DNS server that knows how to obtain the IP addresses of hosts in that domain. This record is used to route DNS queries further along in the query chain. If the C type is CNAME, then the value is canonical host. Pause for a second while I look that word up. If the type equals CNAME, then the value is a canonical host name for the alias host name represented by the field name. I had to look up the pronunciation of canonical. This record can provide querying hosts the canonical name for a host name. If the type equals MX, then the value is a canonical name for a mail server that has an alias host name represented by the field. If the type equals MX, then the value is the canonical name of a mail server that has an alias host name represented by the field name. MX records allow the host names of mail servers to have simple aliases. Note that by using the MX record, a company can have the same alias name for its mail server and for one of its other servers, such as a web server. To obtain the canonical name for a mail server, a DNS query would query for an MX record to obtain the canonical name of the other server. The DNS client would query for the CNAME record. Well, I think that was a load. So I think we need to take plenty of time to review our notes and do whatever research is necessary to understand thoroughly what was discussed. Take care of any assignments that you may have. And when you are ready, come on back for lesson 10.